my class, I had gotten a lot of questions about critical values and p-values and how those worked and related when hypothesis testing. So I wanted to go through a few extra examples. In these 3 examples are going to be hypothesis testing of sample means. I hope to do one on proportions later today. So let's take a look. So what we're doing is hypothesis testing. Hypothesis testing is relating whether or not we can prove the significance of something back to our normal curve, right? So we have 2 hypotheses. We have our null hypothesis, and that's that our mean is no different than the claimed value, right? Let's let K be our claimed value. And we have our alternate hypothesis, okay? And that's that the mean is greater than, less than, or not equal to some claimed value, okay? And what I'm doing when I'm creating a hypothesis test is I'm going to take a sample and I'm going to compare it to our claimed value over the standard deviation of our sample and the size of our sample. Now this should look pretty familiar. This is how you calculate a z-score. This is now referred to as our standard value. So what I want to do, let's say I have a left-tailed hypothesis test. That means I'm claiming my mean is less than some significant value. So let me circle that one. It's not letting me change the pen color. Okay, so we're going to do that the mean is less than K. So here I have my possible value, right, for my sample mean. And what I'm doing with this z-score is I'm finding how many standard deviations, okay, my sample mean is away from the population mean. And what I want is this area, I want it to be small. Okay, if this area is really, really tiny, so less than 0.05, that means that this sample mean wouldn't have occurred by chance. Okay, so this is my p-value. The p-value is the area under the curve that I desired. So this is an example of a left-tailed. Let's take a look at what a right-tailed would look like. So when I have a right-tailed t-test, right-tailed hypothesis test, there's no difference between my mean and some constant value is my null hypothesis. I have my alternate hypothesis that my mean is greater than some K value. And then I have to find my z-score for my sample. But now, instead of previously, where I had a left-tailed, this one's going to be right-tailed. And that leaves me with the area over here. So I want this area to be tiny. And once I find my z-score, I'm going to have to take my z-score and subtract it from 1, right? Because this would be the value of my z-score, this area over here. Because we're in a normal curve, right? So 1 minus my z-score gives me my area. And again, we want this to be tiny. We want this to be less than 0.05 in our one tail. Where things get different is when we work with two tails. When working with two-tailed t-tests, I'm going to be looking at the area in both the right and the left tail. We're going to find our area and multiply it by 2. Our null hypothesis is still that there's no difference in the mean, but our alternate hypothesis isn't that our mean is less than or greater than some given value. It's that our mean is just different. some given value. So K could be less than our mean, it could be greater than our mean. K could be either of these. And what I do in that case is I'm going to find my z-score in either my left or right tail, and I need to multiply my area by 2. The area in one of my tails by 2. This will give me the total area. And again, we want this to be less than 0.05. Okay, so that would show us that it's statistically significant. Now, there was a lot of confusion with critical values. In my opinion, I would ignore the critical values and go straight to the z table and look up the area in the normal curve, right? We've been doing that for multiple chapters now. We should feel really confident when we're doing that. Here are the critical values, okay? And I'm going to show you where these come from. So let's say we're doing a left-tailed t-test. And I want to find the area for some given K. I've got my mean here, right? If I go negative 1.645 standard deviations away from my mean, right? Because remember, that's what the z-score measures. The area in here is 0.05. So if I get a z-score less than negative 1.645, right, it's going to be further to the left, and therefore it's going to have a smaller area. So instead of having to look up in my z-table what the area under the curve is, if I know the critical value, I can just know right away whether or not to reject or not reject my null hypothesis. The same is true for the 0.01 significance level. For my left-tailed test, the area at negative 1.96 standard deviations away from my mean is 0.01. So if I get a z-value even less than that, so further to the left, right, the area is going to be even smaller. So I know I can reject my null hypothesis at the 0.01 significance level. The same is true for our right-tailed tests, except we're looking at the right tail. Remember, it's symmetrical, the normal curve, so it would make sense that the area at positive 1.65, this would have an area of 0.05, and at positive 1.96, this would have an area of 0.01. So again, we're just relating everything back to the normal curve. I would not spend your time focusing on critical values. I would go to the t-table, find the area under your curve, and if it's less than your significance level of 0.05 or 0.01, I would use that information to decide to reject or not reject your null hypothesis, right? So that's for left and right-tailed tests. Let's take a look at the critical values for TwoTails. So our critical values for TwoTails are a little bit different, and here is why. So we're looking at a two-tailed test. So if I have my mean, and I have my standard deviation of 1.96 and 1.96, if I look these values up in the z-table, I find that the area less than negative 1.96 is 0.025. And the area over here as well would be 0.025. So if I add those together, I have 0.05. So that's why the significance level is different for TwoTails, right? Because I'm going to have to multiply my area by 2. When it comes to the 0.01 significance level, if I look up negative 2.575 in the z-table, that's going to have an area of 0.0005. And remember that it's symmetrical, so this also has an area of 0.005. If I take 0.005 times 2, because I've got 2 tails, that gives me 0.01. So that's how I get the 0.01 significance level. And it works two ways. So if my data value, oops, not what I wanted. My data value is more than negative 1.96 standard deviations away, or greater than 1.9 standard deviations away, right? Because I have to look at the area in both tails. I know the area is going to be smaller, so then I would reject. If my area, if my z-score was greater than negative 1.96 or less than 1.96, right? Then my area is going to be greater, so we do not reject. The same thing holds true for the 0.01 significance level, okay? So again, I would not focus on critical values. I would focus on using that z-table that we've been using all semester. I know some of the homework problems did ask you for critical values. The critical values are in the textbook, and they're on pages 314 and 316. I also posted this all over the discussion boards should you need it. So let's go ahead and work through some examples. We're going to do a left-tailed example, a right-tailed example, and a two-tailed example. And I'm going to relate it to the critical values, but I'm really going to show you how we use our z-table to solve these types of problems. So this is the example. You can find it on page 322. It's number 35. So a roper poll used a sample of 100 randomly selected car owners. So that 100 gives us our sample size. Within the sample, the mean time of ownership for a single car was 7.01 years. That's our X bar. With a standard deviation of 3.74 years. That's our sample standard deviation. I'm going to test the claim. So here's our claim by the owner of a large dealership that the mean time of ownership for all cars was less than 75 years. So here's our mean. My null hypothesis is that there is no difference from the claimed value of 7.5 years. My alternate hypothesis is that the mean time people own all cars is less than 7.5 years. This is given to me by the problem. Okay, I have all the information I need now that I have my null hypothesis and my alternate hypothesis. It does not tell us at what significance level we're trying to conduct this test, so we're going to try and check it at the 0.05 and the 0.01 significance level. So the first thing I want to go and calculate is I want to calculate my z-score or standard score. I'm going to take my sample mean minus our population mean over our sample standard deviation over the square root of n. So I take 7.01 minus 7.5 over 3.74 divided by the square root of 100. That's going to give me negative 1.31. So let's relate this back to a normal distribution, because that's what I'd like to do. I have my mean of 7.5. Here I have 7.01, and I'm trying to figure out this value in this green highlighted area right here. That's the area that I want to know. So I take my standard score and I look it up in a z-table. And I find in a z-table that its value at negative 1.31 is 0.0951. That tells me the area right here, 0.0951. Now, we can reject our null hypothesis at the 0.05 significance level if the area under the curve is less than our significance level. So let's take a look. At the 0.05 significance level, can I reject my null hypothesis? No. I cannot reject my null hypothesis because 0.0951 is greater than 0.05, right? I want to find the area of 0.05. So at the 0.05 significance level, I do not reject my null hypothesis. Now at the 0.05 significance level, in the previous slide we saw that has a critical value of negative 1.645, right? Here, we have a z-score, a standard score of negative 1.31. Because our z-score is greater than negative 1.65, it's going to have a larger area than this is, which marks the critical value for 0.05 as the area, right? So we do not reject your null hypothesis. If you cannot reject your null hypothesis at the 0.05 significance level, it's safe to say you cannot reject it at the 0.01 significance level. Right? And the critical value associated with 0.01 is negative 1.96. Okay, and because my value, again, negative 1.31, is not less than the critical value for negative 1.96, it's going to have a greater area, right? The area gets bigger as we go up, and then smaller again. Okay? So let's take a look at a right-tailed example. Change in colors. Okay, so this is the example on page 322, number 36. So according to a study by the CDC, the national mean hospital stay after childbirth is 2.0 days. So this is our national mean. This gives us our population mean. Reviewing records at their own hospital, a hospital administrator calculates the mean hospital stay for a sample of 81 women, right? That's our sample size, after childbirth is 2.2 days, so our sample mean, with a standard deviation of 1.2 days. Assuming that the patients represent a random sample of the population, I want to test the claim that this hospital keeps new mothers longer than the average. Okay, so I'm going to say my null hypothesis is that there's no difference from the mean, right? My mean equals 2.0 days. And my alternate hypothesis is that my mean is actually greater than 2.0 days. So we're going to go ahead and calculate our z-score for here I have 2 days and I have my sample mean of 2.2 days. So I'm trying to find the area over here. This is the area I'm trying to find. Remembering because it's right-tailed, I am going to have to subtract what I find in my z-table from 1. So let's go ahead and calculate our z-score. I have z equals our sample mean minus our population mean over our standard deviation over the square root of n. And a friendly reminder that this equation will be given to you on all exams. You just need to know how to use it and when to use it. So I have 2.2 minus 2 over 1.2 square root of 81, right? Putting together all of our information, substituting it in, and I get 1.5, okay? If I look up 1.5 in a z-table, it has an area of 0.9332. So that's my area over here. In order to find the green area that I really want to find, I'm going to take 1 minus 0.9332, and I get 0.0688. So let's take a look. Do I reject this at the 0.05 significance level? Is my area less than 0.05? No, do not reject. I do not have sufficient evidence to reject my null hypothesis. Okay, I do not reject my H naught. It's important to remember that the critical value for the 0.05 significance level for a right-tailed test is 1.645, right? So if you didn't want to use a z-table and you wanted to use a critical value, because our critical value is less than, because our standard scores are less than the critical value, we do not reject the null hypothesis. And it's safe to say because we don't reject it at those 0.05 significance level, we do not reject at the 0.01 significance level. And that's because its critical value, again, is 1.96. And our standard score is 1.5, which is not less than 1.96. So our last example is going to be a two-tailed example. Hopefully these problems are helping to clarify things for everybody. Again, when in doubt, go to the z-table. That's what I always recommend. So let's take a look at this last example. A random sample of 36 cans of cola is obtained and the contents are measured. The sample mean is 12.19 ounces. That's our sample mean. 36 is our population size. and the standard deviation is 0.11 ounces. I want to test the claim that the contents of all such cans have a mean different than 12 ounces. This word different, not less than or greater than or fewer than or more than, right? That keys us that we're going to have an alternate hypothesis where the mean does not equal something. So in this case, our null hypothesis is that the mean is 12 ounces, and our that's our null hypothesis, and our alternate hypothesis is that the mean is different than 12 ounces. So now I'm looking at a two-tailed test. I've got 12.19 ounces over here. So I'm trying to find the area, let's change colors, over here and the area over here, pretending that I drew this perfectly symmetrical. Okay, so let's go ahead and calculate our z-score. So I have z, which is also called the standard score. So z is x bar minus our mean over the standard deviation over the square root of n. I plug in the values I have. My sample mean is 12.19. Our population mean is what we have defined over here, which is 12, over our standard deviation over the square root of 36. That gives me 10.36. Whoa, that's really high, right? That's a lot of standard deviations away. It's important to remember that when we go to the z-table, for any value greater than, for any z-score greater than like 3.5, the z-tail value is 0.999. Now, I have, this is the z-score for this value, 10.36, right? So what I need to do is I need to find the area over here. Well, I'm going to take 1 minus, because we found the right tail. That gives me 0.001. I'm going to multiply that by 2, which gives me 0.002. So that's my total area. The total area that we get, that's our p-value. And I didn't mention that earlier, and I'm sorry about that, but our area is our p-value, the probability of this event occurring by anything other than, the probability of this event occurring not by chance. So I have a very tiny p-value. Can I reject my null hypothesis at the 0.05 significance level? Yes, we reject our null hypothesis at the 0.05 significance level. Why? Because 0.02 is less than 0.05. Remember that it's a critical value of 1.96 if you were to look it up in that table. And 10.36 is a lot less than 1.96. The same thing is true for the 0.01 significance level, right? You always want to use the smallest significance level you can. So if you can reject something at the 0.01 significance level, mention it, right? The 0.01 significance level, because 0.002, our p-value, is less than 0.01, we reject our null hypothesis at the 0.01 significance level. Notice I don't say we accept our alternate hypothesis. Friendly reminder that as much of a bummer as it seems, there's only rejection in statistics. So we either do not reject our null hypothesis or we reject our null hypothesis. We don't talk about our alternate hypothesis after we define it. So I hope this video helped clear some things up. If you have any questions, feel free to message me, email me, write it on the discussion board. I would be happy to help, and I am here to help, okay? So I hope you guys enjoyed your Easter break, and I look forward to talking with you again soon.